Is my screen visible? Hello?
Yeah, it should be. At least it is visible to me, so others should also be. Okay, any feedback? Message has come. Yes.
Yes.
So hold on, we'll start at one side.
Okay.
Looks like the other class is taking a little longer for the message I got.
So shall we start?
Yes, Aniket, I think you can explain the question, give them 5 to 10 minutes. Okay, then 1:15 also we'll share for this problem.
Okay. So like we are given a PI controller here with a step change of 2. So like we have to like we are given the slope of the output here. So we have to find out our controller parameter, which is the controller gain and the integral time. So basically, you should know the equation which we get after applying the input as your step input and your PI controller transfer function, and we can easily derive this equation in terms of the output, and then we can find out our constants.
So basically the question, so you're given a profile of how the APA controller works, and a similar profile you would see in the notes too, okay? And this is a relatively straightforward question, okay? And you have been given and you have been asked to figure out what is the controller transfer function, technically speaking, the gain and the integral time, the controller gain, which is the proportional gain, and the integral time is something you will have to uh, uh, compute by looking at the figure. So you will have to see that you will have to what you will have to be careful about two things. Okay. Okay, so they are given the set points and things like that, and one is P prime T. So prime, you have to assume that, so generally prime is something in terms of deviation variables, right? Unless otherwise specified, okay, it is in the deviation variable, so you'll have to take that into account and solve this problem. If there are no questions, any questions, otherwise you please try yourself. Maybe 112 or 115. So how many questions are there in this tube? 1, 2, 3, 4. So let's take 15 minutes each for every question. So 115 will get back to you. Please try solving yourself. Aniket, I think you can help them with the steps. Go slowly, explain every step. Okay.
Okay. Okay, so like first, this is the expression for the output in case of a PI controller. So basically Kc is your controller gain here and tau I is your integral time. So these two are the parameters which we are supposed to find out. So like this is in terms of our original variable. So first we'll subtract it from the steady state value. So this will convert it into a, you can say, your deviation variable. So now we are given that we are that there is a step change of -2. So basically 2. So from the set point, it will be a change of -2. So our error here will be it will be a constant function only with respect to time. So it will be just -2, and when we'll put -2 and do the integration, so we can get our equation for the output in terms of deviation variables as kc into -2 by tau r t. So like as we can see from the graph here that the initial y-intercept is equal to 6. So that will be equal to -2 kc according to our equation. And similarly -2 kc by tau will be our slope. So we can just equate these two parameters and we can easily find out kc equals to -3 here, and from here we can find out tau I equals to 5 minutes. So any doubts in this one?
Could you able to solve by yourself and got stuck? At least the steps were right. Hmm? Any issues? How many of you are here? Around 8, but I think I hope you are able to solve it, I guess. Anything, any step that is not clear? Ashutosh, Bhavya, Deepak, Dinesh, Matulika, Vinayak. Are you all with us?
Yes, sir.
Okay. Okay, so then it's fine. Just relatively a smaller problem. And now you can go to the question 2 and explain it.
Okay, so we are given another PI temperature controller here, and which is currently giving an output of 8 milliamperes, and its set point is set to the nominal process temperature, which should be there. So we have introduced a set point change of 2.5 milliamperes. So we are supposed to again find out the controller gain parameter as well as the integral time. So like from this data, basically in an earlier question we were given the plot itself, and in this question we are given these data points. So basically you can again find out the similar expression, and we can evaluate these constants again.
So this is exactly, so here, so the question 2 is like a numerical data driven equivalent of question 1. Instead of giving them the profile, you are given with a set of data. And again, you will have to apply the same set of principles, okay, and calculate the details regarding whether it is direct acting and reverse acting, right? Yeah. So that question, you know what is the definition of the direct acting? If generally Kc of the system is what you call negative, it would be a direct acting control. So you have to compute the Kc and tau and look at the sign, because tau I cannot be negative because being the time variable, integral time, right? So check that and let us know. Again, we that should be fine. We can wait till 125 or so. So you check yourself, try solving yourself and get back to us. Or at least try attempting the steps, so that everything would be clear.
So shall we go ahead?
Yes, I think it should be okay.
Okay, so it was a pretty similar problem. So first we were like the points when plotted will give a similar kind of curve as according to the previous question. So again, in like we can again derive that same formula by like basically our output upon input should be equal to the transfer
Excuse me,
function
sir.
of our, yeah, yes.
Sir, cannot we like discuss the questions before you show the solutions? Because in that way, I think it would be more beneficial.
I guess like what like I have already explained the approach, like it was similar to the first one. So what kind of,
Okay, so who was this?
Sir Vinayak.
Vinayak. Okay, so what Vinayak want, you want you explain again, explain the question once more and go to the solution. Is that what you say?
No, sir, what I was suggesting was that in a class prior to minor, you discuss the questions before showing us the solution or before like solving it. So cannot we do something similar like that?
I did not understand.
Sir, maybe we can discuss the question before sir show the solution because
so like you want us to explain the question first and then move on to the solution, right?
Is that what? So I did not understand. So exactly what do you need? So you want to explain the question a little bit more, then go to the solution, or what?
sir, what I'm trying to say is maybe we can discuss the question between ourselves and then go to the solution.
Okay, so you are saying you would so if I understand you correctly, in the sense that we would have an informal discussion first. How do you
Yes, sir.
solve
Yes.
and how do you not solve this? Then you go and show the solution. Is that what
Yes.
you are trying to say? Correct?
Yes, sir.
Okay, so then you can welcome idea. So maybe let's start from you itself.
Yes, sir.
So
We can start from the next question.
no, I think let's go ahead. So maybe I think. No, so maybe just to get a flavor. So maybe you can just think. Let's start with you only. So you can just explain what do you feel? How you would if you are solving the problem, what all things you do?
Yes, sir. So basically, this is a direct application of PI temperature controller, and we can directly refer it from the graph that we solved above, and it is also given in that the intercept will be due to the proportional part and the slope will be due to the integral part. So by taking the change at t equals 0, which is 1.3, we can get the proportional constant Kc, and by calculating the slope we can get tau or Kc by tau 1.
Okay,
And if the slope comes to be negative, then I think it will be reverse acting.
perfect. So any other what you call additional points anyone needs to add? Hmm? Okay, so thanks, Vinayak. Now, what you call, Aniket, you can explain the solution in more detail.
Yes, so like as Vinayak explained, like this approach is very similar to that only. So basically what we are in this like we can solve it in other ways by considering the transfer functions here. So we can have the our output upon input should be equal to the transfer function of our controller. So as for a PI controller, we will have a controller gain as well as a integral time. So our transfer function would look like Kc into 1 plus 1 by tau is. So and our it is given that it is a step change. So our input will be m upon s in Laplace variable terms. So once we cross multiply it, our output in terms of deviation variables will be kcm by s plus kcm by tau s square. So when we'll convert it into the time domain, so our equation will be exactly similar to what we obtained in the first question. So again, as Vinayak explained, so yeah, our y-intercept, which is kc into m, will give us our kc, and kc m by tau will be our slope. So these two, and from the data which is provided to us, our y-intercept is equal to minus 1.3, and from the slope we can calculate the slope as minus 0.035 milliampere per second. So plugging in just all those values, we can easily find out our Kc and tau I. So it is actually the opposite case, Vinayak. Like if the Kc is negative, then our controller is direct acting, and if it is positive, then it will be reverse acting.
Cool. Any clarification further on this? Thanks, Aniket. Okay, so if there are no more questions, let's go to the third question. And what we'll adopt the strategy. Aniket will explain the question for a couple of minutes, then you can independently think. Then we can either invite one of you to kind of present your approach to solve this, or someone can volunteer, and finally we would reconcile. Okay, thank you.
Sir, in this question, case is negative, so you said that it will be direct acting. So is this like by definition?
So see, so generally, if you look at so the gain versus what you call the direction of the gain is negative, it tend to act direct, because see, direct acting has a connection with the original process variable. Okay, so if the process variable is keep on increasing, okay, fine, that is, and if you keep on keep on increasing the control gain, so you won't be able to control it, no, because both of them will go in the same direction. For instance, you are going, if there is if the tank level is increasing above the set point, correct, and you are also and your controller is also giving more instructions to the valve, so that valve is increasing, open more. So what would happen? Uh, your eventually you will not be able to control. So so in this sense, what so if the process variable is increasing, okay, and you would like to reduce what you call the effect of it, you will have to have the if you have to have the gain value to be negative. So in this context, it is a direct acting controller. You got it?
Yes, sir.
So yeah, I think we can go ahead, I suppose. So maybe next question.
Yes, sir. So in this question, we are given a PID controller instead of a PI controller. So like it is at the steady state with an which is currently giving an output of 12 milliamperes. So again, we have in this time we are giving it a, ramp input of 0.5 milliamperes per minute, and the current settings of the controller are already given to us. Basically, KCR controller gain is 2, and our integral time is 1.5 minutes, and differential time constant is 0.5 minutes. So now we are supposed to find out the expression for the controller output. So like this is a kind of a reverse question. Like first we are in this case we are given the controller parameters already. We are supposed to find out the output, and we have to repeat the same case in case of a PI controller as well. So like this should be easily solvable if you can just try out once, and if you face any doubts you can just ask us.
Again, just to say, you're given with the characteristics of the controller, okay, and some strategy, like some initial conditions, how are the things going to get started, and your the current setting is given, and you have been asked to find out the controller expression in P of t. So see, the difference here is that most of the controller expressions what we have learned is in the transfer function domain. Here you are asking for in the time domain. So so it's you would have to kind of
Do we have
encounter a
to take inverse Laplace?
yes.
Like,
So you would have to play with the Laplacian Laplace
yes.
variable and figure out from S to T. So this is the That's only the additional thing that you're going to do in this problem. Rest all is going to be the same. So maybe continue and we will discuss this for 145. Maybe let's gather. Aniket, maybe. So who wants to volunteer this, or maybe we can even allow the screen sharing and present the result. Somebody can?
Sir, I actually solved it using online calculator and got the answer for the first part.
Okay. Anybody has a handwritten solution or something like so that you can share your screen and this thing? Anyone? So that we'll initiate a discussion. Otherwise, again, Aniket will have to share his screen and present the result. Okay.
Yes, sir.
Okay, then go ahead, Aniket. If some people have solved, please verify that you are getting the right answer.
Okay. So so we were given this ramp input of 0.5 t. So in terms of our Laplace variables, it will be 0.5 by s square. So again, similar to the last problem, we are given the in this case we are given the controller parameter. So we know the transfer function of the controller, and we also know the input. So we need to find out the output. So basically we'll just cross multiply and take the anti-Laplace of this entire term on the right hand side. So this will give our output as 12 plus 1 by 3 t square plus t into 0.5 of into s of t. So like were you getting the same solution from the using the online calculator?
Yes, sir.
Okay. So now, like in the second question, it is just asked that we have to calculate the same for a PI controller. So we can easily do that by just setting tau d equals to 0. So yeah, so basically this last term will not be there, and the remaining all the expression will be same exactly. So this was just the change required. So any doubts in this one, anyone?
No, sir.
Any other participant? Okay, so then let's look at the last problem, I guess, for today's bit.
Okay, so this is a different problem than the others which we have solved till now. So we are in this case we are given two controllers in parallel arrangement, and this is a PD controller. So we have to basically first we need to like we are given one transfer function which is for a controller, and we are also given the we have to make it in form of two parallel controllers arrangement. So we have to basically find an overall controller, and then we have to compare our kc tau d and alpha with respect to k1 tau 1 and k2. So this is our task to first get the values of k1 tau 1 and k2 in terms of kc alpha and tau d, and then we can further evaluate those expressions, and then we can verify them using some values that we have solved it correctly or not. So the task is just to find out the transfer function in case of a parallel arrangement and compare it with the transfer function given above. So basically these are just mathematical manipulations only, so you can just try out this one. Any doubts in the understanding of the question and what is the question trying to ask?
Sir, so basically we have to relate the values of K1, tau 1, K2 with the expression that is given in the question P dash over E.
Yes, exactly.
Absolutely. So see, any physically realizable form of the PD controller would have the following form, okay? And then you are given with a parallel arrangement of controllers, okay? No, parallel arrangement of systems. And now your question is, can we kind of correlate this with the uh, given condition? So you'll have to go from your parallel structure, okay, then compute K1, K2 to obtain the desired value. So you'll have to do some sort of equation between the standard form and whatever that you are given to you, and I think that's all about it.
Sir, I just wanted to clarify something.
Go ahead.
Sir, it was regarding the syllabus for the quiz. Sir, will we be asked syllabus before the minor, which is notes 5?
So the two tutorials, last two tutorials.
All right, sir.
So this one and the one before. So these are the two quick things that you'll have to look at. So just one more thing, okay. So previous the question content may be last two tutorials, but like you may have to use some of the techniques that you have learned previously also. In the sense, you may be able to understand what is damping coefficient because it's a gradual development, no? So when you are dealing with second order systems, you should know what is zeta. So those things would be always there, but you would not be using any particular results from there. So overall understanding maybe the needed. For instance, the inverse Laplace, that is anyway you are learning from the first class, that you may have to do. So as far as the core contents concerned, this tutorial and the previous.
Yes, sir. All right.
Or yeah, I think we shall discuss, I guess. Is this a good time to discuss, or you want to?
Yes, sir.
Okay. So someone would like to volunteer and explain the problem in detail and what you have to solve. Then maybe Aniket can explain towards them.
So the problem is really very straightforward. All we have to do is add the transfer function given in the figure and then compare it with the form which is given in the question. And then we can get the desired values of alpha, tau d and kc.
Okay, cool. So maybe Aniket, now you can share the solution and check.
Yes. So yeah, like it was pretty the same as he explained. So yeah, so basically we just have to add these two, and we can just convert this expression in terms of the original expression which was given in the question, which is kc tau d, alpha tau d. So basically from here we can compare like our kc should be equal to k1 plus k2, and our
Yeah,
tau
go
d
slow.
will.
Go a little slow so that. Yeah.
Yeah, so like basically we were supposed to add these two transfer functions. So this was a first order transfer function. This was just a constant. So we'll be adding these two, and we can like our denominator is already same, and for the constants we can just take it like k1 plus k2 will be a constant, so we can just take it out. So we can get a 1 on the numerator here as well. So like when we compare this expression with the expression given in the question, so we can see that Kc should be equal to K1 plus K2, and tau 1 should be equal to alpha tau d. So from here we can, or all, and also tau d should be equal to K2 K2 tau 1 by K1 plus K2. So like we have just put it here. So B in the second part we are just doing that only. So Kc is equal to K1 plus K2, and a tau 1 is equal to alpha tau d. And the third inference is tau d should be equal to k2 tau 1 upon k1 plus k2. So as in the from the second expression we can put in tau 1 equals to alpha tau d. So hence we can like the tau d on both sides will be divided. So we can get k2 alpha upon k1 plus k2 as 1. So again, doing some mathematical manipulations, we can easily derive that k1 should be equal to k2 into alpha minus 1. And as we know that k2 is also equals to basically k1 plus k2 equals to kc, so k2 is equals to kc minus k1. So again, we when we put in this value, we can derive that k1 is equals to alpha minus 1 upon alpha kc. And similarly, like we can also derive k2 by putting k1 plus k2 equals to kc. We will get kc should be kc by alpha, like k2 should be kc by alpha. So and yeah, so and tau 1 and tau d are already related. So these are the three expressions which will be required. So any doubts?
Any issues? Okay, so
No,
this chapter is relatively a straightforward chapter. So, but make sure that you try to understand it carefully, and also the previous chapter where we have given the data-driven modeling based on what they call the data. So please prepare well and come for the quiz tomorrow during class hours. Okay. So I think
sir,
that's
I
all
had
about.
to ask one thing.
Please go ahead.
What sort of questions can we expect from Note 6?
Note
Because
6.
it is
Note 6
very
means what? The previous
the
one.
chapter which was where we used regression and fitting model,
Huh,
because
so I
some
think
part of it is very mathematically rigorous.
no. So you can look at the two problems. No, last time you cannot create arbitrarily too many of questions. So maybe given a profile, calculate something, or given a data, you compute something. Got it, right?
Sir, if I'm not wrong, then the previous tute was based on that, uh, based on some other concept and not this.
No, maybe no. That contains these things, no. Except that I think linear regression might not be there, but most of the other things were there.
Sir, most of like the previous tute was based on notes 5.
Yes,
And
sir.
But that contains 2-3 questions from Note 6 too, right?
No, just
No,
like
sir, I don't think so.
the last one.
Let
In
me
short,
open.
we really haven't had any tutorial
Sir, the
for
last two
that
questions which
chapter.
we
So if I
did.
understand, last one or two questions are related to the chapter 2.
Yes,
Yeah.
sir.
Okay, so yeah, Q3 and Q4.
Okay,
Got
sir,
it?
I see it.
Hmm?
Yes, sir.
Yeah, so you can imagine similar type of questions. So there is not many scope to make this thing too much convoluted. Yeah, and also you can look at the problems that is solved in the textbook. So that would also give you an idea. I think even some of the questions have been taken from the textbook, I think. Okay.
Yes, sir.
Okay then, guys, all the best. See you tomorrow for the exam. And meanwhile, if you have any doubt, feel free to write to us. Bye bye.
Right, sir. Thank you.